Welcome to this explainer. I am your host, and I'm incredibly excited to get into today's session. We're looking at the Cambridge Mathematics exam strategy, specifically focusing on syllabus code 0580. Now listen up, because we are going to look at mathematics through a slightly different lens today. When most of us think of math, we picture absolute, rigid precision, right? The idea that there is one single, perfectly exact right answer. You see students all the time, let's call one Alex, who just overload their exam papers with raw, unrounded facts, no analysis, just a massive data dump. Or you see students like Sam, who rush through, completely miss the command word requirements, and lose huge marks. But the truth is, in real-world mathematics, and especially on these Cambridge papers, absolute precision isn't always necessary. Honestly, sometimes it's the exact opposite of what the examiner is looking for. Today, we're building your real-world mathematical toolkit. We'll explore how to handle shifting proportions and how to absolutely master the art of rounding, approximation, and estimation so that you can tailor your answer to fit the question perfectly. No loose threads. You're going to navigate complex numbers with total confidence. Let's get started. Okay, let's look at our map for today. First, the logic of inverse proportion. Second, the rules of rounding. Third, mastering decimal places. Fourth, understanding significant figures. And finally, number 5, the power of estimation. Let's kick things right off with Section 1, the logic of inverse proportion. Before we tackle the math, I want to take a quick second. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the logic. Normally, we deal with direct proportion. When one thing goes up, another goes up. You buy more apples, you spend more money. Simple. But inverse proportion flips that entirely on its head, and examiners love testing this. In an inverse scenario, an increase in one quantity actually causes a direct, measurable decrease in another. Look at this question. If 8 people can pick apples from an orchard in 6 days, how long is it going to take 12 people? I really want you to visualize this. Think about the relationship. We're bringing in more workers. If we increase the number of hands on deck, the time it takes to finish the job literally has to shrink, right? More hands, less time. That's the essence of inverse proportion. And the math to solve this is brilliant. If 8 people take 6 days, imagine just one poor person doing it all by themselves. It would take them 48 days. That's just 6 multiplied by 8. So if we now have an army of 12 people, we take those 48 total days of work and divide them by 12. That gives us exactly 4 days. Now let's apply that exact same logic to speed and travel time, a classic exam scenario. Here we have a cyclist. She's averaging a speed of 27 kilometers per hour, and it takes her exactly 4 hours to complete her route. But what if she wants to crush her personal best? What if she wants to finish that exact same route in just 3 hours? Think about it. Her time is decreasing, so logically, her speed has to increase. She's got to pedal harder. If she wanted to do the whole thing in just 1 hour, she'd have to cycle at an impossible 108 kilometers per hour. We get that by multiplying her original 27 kilometers an hour by the 4 hours it originally took. To figure out the speed for a 3-hour trip, we divide that total 108 by 3, and boom, that tells us she must increase her average speed to 36 kilometers per hour. As time goes down, speed goes up. Perfect inverse proportion. Moving right along to Section 2, the rules of rounding. Look at this number on the screen, 28,617. When you're dealing with massive real-world situations, exact numbers like this are rarely reported because they actually obscure the main takeaway. Imagine this is the number of people attending a massive international gymnastics competition. If you're a journalist writing a headline, reporting exactly 28,617 attendees is just clunky. It's a heavy, cumbersome piece of raw data that's actually kind of hard for the human brain to quickly process and remember. An examiner doesn't always want the raw data either. This is where rounding comes in to save the day and tighten up your answers. Watch how this exact number transforms depending on the level of accuracy we actually need. If we just want a really broad, big-picture estimate, let's say to the nearest 10,000, we round 28,617 up to 30,000. Why? Here is the absolute core rule of rounding. You always look at the next digit to the right of your target. If our target is the 10,000s column, the 2, we look next door to the right at the 8. Because 8 is 5 or larger, it bumps that 2 up to a 3. Now what if we need a bit more precision, say to the nearest 1,000? Our target is the thousands digit, the 8. We look next door to the hundreds digit, which is a 6. 6 is 5 or larger, so we round up to 29,000. But look what happens if we round to the nearest 100. Our target is the 6. We look right next door to the tens digit, which is a 1. Since 1 is less than 5, we do not round up, we round down, giving us a super clean 28,600. It's the exact same reality, just reported at different, more functional resolutions. All right, let's step into Section 3, Mastering Decimal Places. The rules we literally just walked through for whole numbers apply directly to fractional numbers too, but the context shifts strictly to the right side of the decimal point. Decimal places. You'll see it abbreviated as DP on your exam papers constantly. Refer to the specific number of digits written immediately after a decimal point in a mathematical value. I am emphasizing this because students, especially our friend Sam who rushes through questions, constantly confuse decimal places with significant figures. Decimal places are purely about geography. Ask yourself, how many spots to the right of the dot are we keeping? That's it. Let's run a quick step-by-step. Say the command on your exam says to write 7.864 to one decimal place. Step 1. Identify your target. That's the very first digit after the decimal point, the 8. Step 2. To figure out what happens to that 8, we look one single spot to the right at the second digit. That's a 6. Step 3. Because 6 is 5 or more, we trigger our golden rounding rule and round that first digit up. So 7.864 becomes a clean, tight 7.9. Now conversely, if you had a number like 5.574 and you needed to round it to 2 decimal places, you'd target the 7 and look at the third digit. Since it's a 4, which is less than 5, that 7 stays exactly as it is. Your answer is just 5.57. It is a beautifully logical system once you internalize the pattern. And hey, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Let's transition over to Section 4, Understanding Significant Figures. Okay, focus up because we are entering territory that trips up a massive percentage of candidates. Significant figures, or SF, unlike decimal places, honestly do not care about where the decimal point is positioned. Significant figures are the digits in a number that carry a meaningful contribution to its overall measurement precision. You always start counting from the most significant value. That means the biggest, heaviest chunk of the number. Think of a number like 43.25. The 4 is actually the most significant figure of the whole bunch because it literally represents 40 whole units. The 5, way down at the end, it's the least significant because it merely represents 5 tiny, microscopic hundredths. We care about the big, impactful digits first. To really see this in action, check out this side by side. If we want to take 43.25 down to 3 significant figures, we count the 3 heaviest hitters, the 4, the 3, and the 2. To decide the fate of that 2, we look at the 4th digit, the 5. 5 or more means round up, so we get 43.3. Pretty straightforward, right? But look at the right side, 0.0043. This is the ultimate exam trap. If we want 0.0043 to one significant figure, you do not count those leading zeros. Leading zeros are literally just placeholders. They hold the door open. They have zero mathematical significance when we talk about precision. The very first truly significant figure in that sequence is the 4. Because the question only wants one significant figure, we lock onto the 4, look next door at the 3. It's less than 5, so no rounding up. The answer is simply 0.004. You scan from left to right, find the first non-zero number, and start your count right there. Finally, we reach Section 5, the power of estimation. Now, you might be sitting there thinking, why do I need all these approximation tricks when my calculator does the heavy lifting? Well, let's say you punch 4.64 divided by 2.3 into your scientific calculator. It is going to confidently spit out 2.0173913. It will give you as many decimal places as its LCD screen can physically fit. This is exactly where our imaginary student Alex loses marks. Blindly trusting a screen and writing down all 8 decimal places without checking the logic is a massive trap. In almost no real-world scenario, and certainly on very few exam questions, do you need accuracy down to 7 decimal places. It's just noise. By applying an appropriate accuracy of 3 significant figures, which is a phenomenal default standard, that messy, chaotic calculator sprawl on the left transforms into an elegant, properly rounded 2.02 on the right. It is readable, it's confident, and it gets the marks. I want to put you on the spot right now. Look at this calculation on the screen. 57 multiplied by 246. If I told you to solve that right this second, hands off the calculator, your brain probably tenses up a bit. It looks heavy, it looks like it needs scratch paper. But applying the estimation rules we've just learned completely rewires how you handle this. How would you quickly estimate this before even touching a button? Watch how we make this intimidating problem completely digestible. Step 1. Let's take that awkward, jagged 57 and round it up to a straightforward, friendly 60. Step 2. Let's take 246 and round it down to a nice, simple 200. Sure, you could use 250, but using 200 makes the mental math practically instantaneous. Step 3. Now just multiply 60 by 200. You know 6 times 2 is 12. Toss on your 3 zeros, and boom, you instantly have a highly functional estimate of 12,000. By smartly rounding our starting numbers, we took a complex problem and solved it mentally in about 3 seconds. And here's the genius part for your exam. If you then use a calculator and it gives you something like 1,400 or 140,000, you instantly know you've keyed in the wrong number and you can fix it before losing the grade. To wrap up today's toolkit, I want to leave you with these absolute golden rules directly from the Cambridge syllabus. This is your cheat sheet. When you are sitting in that exam hall or even dealing with practical real-world measurements, these are your default settings. Rule 1, non-exact calculator outputs are almost never needed in full. Do not write down 10 digits. Rule 2, if your final answer involves measuring lengths and the command word doesn't specify otherwise, your default setting is to round to 3 significant figures. Rule 3, if you are calculating angles, you must default your answer to 1 decimal place. Sticking to these 3 rules guarantees your work is professional, precise, and perfectly aligned with what the examiners are grading. We've covered a tremendous amount of strategy today, from the shifting logic of inverse proportion to the strict, undeniable rules of rounding, decimal places, and significant figures. You now know how to look right past the clutter of massive data dumps and long calculator readouts. So I have to ask you, the next time you face a complex calculation under exam pressure, are you going to be like Alex and blindly trust every single chaotic digit on that screen, or will you take total control and use your new approximation toolkit? Listen, students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, AC Exams, at ACExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at ACExams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. AC Exams, your Cambridge success starts here.